Hello everyone. In the previous videos, you have learned how to use the package R to summarize datasets, both in terms of numbers as well as by means of graphs. The main objective was to find out what kind of features the data possesses. However, the numbers and graphs that R produces can also be used to select a suitable probability distribution to model the uncertainty that is involved when one is collecting observations. Let us consider a dataset consisting of the heights of 111 males in centimeters. Each observation is the length of a randomly chosen male individual. Now beforehand, the observations resulting from measuring the heights of randomly chosen males are uncertain. And our dataset is just one possible outcome of that experiment. Now the way to model the uncertainty in such a situation is to consider the observations as realizations of random variables. The first observation, 180, is modeled as being the realization of a random variable x1. The second observation, 173, is modeled as being the realization of a random variable x2, and so on. And finally, the last observation, 176.9, is modeled as the realization of a random variable x111. Now, assuming that the resulting height of each randomly chosen male is obtained under the same uncertainty, the random variables are assumed to have the same probability distribution. And assuming that obtaining the height of a particular male is not influenced by the heights of other males, the random variables are also assumed to be independent. Summarizing, the observations are modeled as being realizations of independent random variables x1 up to xn with the same probability distribution. This distribution is called the model distribution, and the model assumptions made about the uncertainty are described in a so-called statistical model. Now, this model distribution is yet unknown, but having made this connection, we can use our observations at hand to provide more information about this distribution. For example, in probability theory, you have learned the law of large numbers. It says that the average of independent random variables with the same probability distribution converges in some sense to the expected value of this distribution as the sample size gets larger. The consequence is that if we generate numbers independently from the same distribution, their average should be close to the expected value of that distribution for large sample sizes. Now let me demonstrate this in R. We generate 100 numbers from a standard normal distribution which has expected value 0. When we repeat this, we see that the averages of the generated samples are indeed close to 0. And if we generate more numbers, say 1000, the numbers get even closer. Now this can be illustrated in this figure for a sequence of averages for growing sample sizes from 1 to 1000. But this property also works the other way around. Because we model our dataset of height as numbers being generated independently from the same model distribution, the average height should be close to the expected value of this distribution. And therefore, based on this dataset, the expected height of a male individual is about 179 centimeters. Now this illustrates that the average of the observations gives an idea of the expected value of the model distribution. In fact, several numerical summaries of the dataset correspond to similar features of this distribution. Well, here's an overview of some of these similarities. For example, the sample median of the observations will be close to the 50th percentile of the model distribution, and similarly for an empirical quantile. The sample variance will be close to the variance of the model distribution, and similarly for the sample standard deviation. And finally, if we have paired observations, that are generated from the joint distribution of a random vector x, y, then the sample correlation coefficient computed from the observations will be close to the correlation between x and y. In addition to numerical summaries, also graphical summaries correspond to graphical features of the model distribution. For example, if we generate numbers independently from the same distribution, the histogram of these numbers will be close to the probability density of this distribution for large sample sizes. So here we generate 100 numbers from a standard normal distribution and plot the histogram. Now, when we scale the histogram to have area 1 under the curve, it matches the shape of the standard normal density. And for larger sample sizes, the match gets even better and better. Again, this property also works the other way around. Because the heights are modeled as numbers being generated independently from the same probability distribution, the histogram should reflect the density of this distribution. Now, as the histogram of heights has the shape of a normal density, the normal distribution seems a suitable candidate as the probability distribution for the height of a male individual. The QQ plot also confirms this. Now, moreover, we can use our observations to determine reasonable values for the parameters mu and sigma squared of the normal distribution. Because the parameter mu is the expectation, the example earlier in this video shows that the average height, about 179 centimeters, seems a good choice for mu. And similarly, the sample standard deviation, 6 centimeters, should seem a good choice for sigma. Now, when scaling the histogram such that it has area 1 under the curve, it can be compared with the density of a normal distribution with mu and sigma equal to 179 and 6. Now, in view of the fact that this sample size is only 111, the match is reasonably good. Now, the fact that the normal distribution is a good model for male height is not a surprise because of the Semper-Limit theorem that you have learned in the probability theory course. It states that the probability distribution of the sum of independent random variables can be well approximated by a normal distribution. Now, since the height can be seen as the sum of many little growth spurts, a normal distribution can be expected to be a good model. Now, this concludes the last video of this week. And in this video, you have learned the statistical model for a dataset. This model considers the values in the dataset as numbers being generated from the same probability distribution. You also learned that some numerical and graphical features of the dataset are linked with particular features of this distribution. Now, please play around in R with other datasets to familiarize yourself. As always, you will find corresponding exercises after this video, which will let you do exactly this. Enjoy!